In this course, we're going to be doing quite a bit of circuit analysis, high-frequency circuit analysis. And that might sound disconcerting, but one thing that you can bear in mind is that we'll always have the same source, the same excitation of those circuits. And that excitation is that of a sinusoid. A voltage, for example, for a source, a function of time, but a function of time that's well defined with three real valued parameters. So we look at this sinusoid, this voltage is a function of time. We see that it is proportional to the cosine of some phase argument. The cosine, remember, always works on phase, and this phase is a function of time. Not a complex function of time, a very simple one, a phase which is directly proportional to time. The proportionality constant is omega, the radial frequency omega. And of course, if you do a dimensionality analysis, you find that omega must have units of radians per unit time or radians per second. So omega, radians per unit second, times t in time will give us radians, the proper argument for the cosine operator, that trig operator. The voltage ultimately is proportional likewise to this function, cosine function of time, and that proportionality is the magnitude. So we have three constants that define this sinusoid, and every sinusoid that we're going to use in this class. The magnitude, which is a positive real value. Omega, and we're going to assume what we call physical frequencies here, so omega likewise will be positive and real. And finally, a phase value, which essentially shifts the sinusoid function right or left in time depending on its value. Three real value functions completely parameterize this source. Every source will be of this form, and then therefore every source you need to only determine the three real values, positive real values that will make up this sinusoid. Now, someone tweets in, one of the students here that's listening tweets in this question. They say, why do we always seem to use sinusoid in electrical engineering? Why don't we use some other function, square waves or triangle waves or some other, smooth function of time other than sinusoids? Are we just nerdy engineers who like the concept of using trig functions whenever we can? Well, it turns out there's a very important reason why we use sinusoids, and they are ubiquitous in electrical engineering. We see them in Fourier analysis, certainly in power. If we look at the 60 hertz signal coming out of our wall, that is a sinusoid as well. Why do we keep bumping into these sinusoids, and why do we keep using them in electrical engineering? Well, it's because of this very special property. One thing I want to point out, go back, I neglected to say, in this class with the sinusoids, notice that they are on forever and will be on forever. There's nothing here that says it turned on at a certain time or will turn off at a certain time. So that's part of the assumption that we'll do in all of our circuit analysis, that sinusoid has an infinite time, on forever and will be on forever. All right, let's go back and look and figure out what is the special property that sinusoids possess. So what is the special property that sinusoids possess? It turns out that sinusoids are the eigenfunctions of all linear time invariant systems, and therefore the eigenfunctions of all linear time invariant circuits. Now, the question is, what does that mean? First of all, I'll put a caveat on there. At least I get email from mathematicians, and I have gotten email in the past from them that are upset about my assertion that sinusoids are eigenfunctions of linear time invariant circuits. The reality, as we'll see later, is that the real true eigenfunctions are complex exponentials. But the real part of any complex exponentials, we'll see in a second, is a sinusoid. So sinusoids are the real part of the eigenfunction of all linear time invariant functions. Okay, what does that do for us? Why do we care? Well, we can explain it probably best with an example. Let's say we take a sinusoidal voltage and use it to excite a linear time invariant circuit. We use it as a voltage source, some sinusoid, again, of the form on the previous page. Three real value numbers that describe it. One real value for its magnitude, another real value for its radial frequency omega, and a third for its relative phase phi. As we go along the circuit and we look at every point in that circuit, across any resistor, the voltage across any resistor or other linear element, the current through any linear element, what we'll find at every point is it will have essentially the same form as the source. It will be a sinusoid with frequency omega. If we excite the circuit with a sinusoid of 1 gigahertz, 1 billion cycles per second, and therefore its frequency omega would be 2 pi times 1 billion in terms of radial frequency. Multiply the frequency in hertz cycles per second by 2 pi, and that gives you the radians, omega in radians per second. So we excite it with a 1 gigahertz signal, and we go around and we look at every current and every voltage in that linear circuit. And what we find at every single spot is a sinusoid of precisely 1 gigahertz. We don't find a different function of time. We don't find a sinusoid that is of a different frequency other than 1 gigahertz. Once we excite it with a sinusoid of 1 gigahertz, we see a sinusoid of 1 gigahertz everywhere manifest itself at every current and every voltage within that circuit. Now that might seem obvious and unremarkable to you that there's a sinusoid of the same frequency at every location on the circuit if it's excited by a sinusoid of a specific frequency. But if we go look at some other functions of time, let's look at a square wave, for example, like this over here, and let's say that is our source, and we excite a linear time-invariant circuit, one made of inductors and capacitors and resistors, for example, and we go around the circuit and we look at the different currents and different voltages at each location. What we'll find is almost certainly those functions of time will not be a square wave. Those functions will be different. They'll be distorted. We call this linear distortion. They're not distorted because of any nonlinear device like a transistor or a diode that may be perhaps saturating. No, it's because that we excited the signal without a sinusoid with a different function than a sinusoid, and that linear circuit will change that function into something different. And that's true essentially for every function that we use to excite a linear time invariant circuit, with the exception, of course, of a sine wave. Let's say we excited a linear time invariant circuit, this one here, for example, and we excite it with some arbitrary source as a function of time. And what we want to go through and measure the voltage at different places on the circuit, voltage across different elements. We could measure the current across different elements, and we want to know what are these functions of time with respect to the original source. Well, again, if this original source is not a sinusoid, then we find that it is some arbitrary function of time different from the form of the original source. How would we determine those answers? Well, we'd have to go through and solve differential equations relating the source voltage, for example, with respect to time to current I2 with respect to time. We could perhaps simplify that differential equation solution, simplify it by applying Laplace's transforms and then going through and solving the problem that way. Regardless of how we choose to solve the problem, it's not particularly straightforward or easy to determine the arbitrary functions of time at each point in this circuit with respect to the original source. Again, not only will these solutions be different than the original source, each of them will be different from each other. None of them will look quite the same, generally speaking. Unless, of course, we excite that circuit with a source which is a sinusoidal function, a sinusoid function that has a frequency omega, a magnitude, and a relative phase. In that case, we know we'll find a sinusoid that exists at every single location in the circuit of precisely the same frequency of that as that of the source. At every location, thus, we find, again, a sinusoid if we excite the source, or the circuit, rather, with a sinusoidal source. The question is it exactly the same function as the source? And, of course, it's not quite exactly the same. It is a sinusoid at every location, but remember, there are three parameters that define a sinusoid: its magnitude, its frequency omega, and its relative phase. If we excite a circuit with a source with a certain magnitude and frequency and relative phase, what we'll find is that each location in the circuit, the currents and voltages, also would be a sinusoid of precisely the same frequency omega. That one parameter is invariant as we move from element to element within the circuit. Omega stays the same. It's precisely the same as the source. If the source is 1 gigahertz, 2 pi times 1 gigahertz is omega, then that is in fact omega at every single place in the circuit for all currents and voltages. What will change, however, from location to location of the circuit is the magnitude of that sinusoid and the phase of the sinusoid. Those other two parameters are not invariant as we move across the circuit. They will change and be different from the source and likewise different from each other. In other words, different from element to element to element. For example, if we go back to our circuit that we looked at earlier. In this case, we're going to assume that we excite that circuit with a source, a voltage source, which is a sinusoid. A sinusoid of some frequency omega, and of course some magnitude and some phase. If we look at the voltage at each location in the circuit, and we look at the current at each location in that circuit, what we find is, again, they are all sinusoids. All sinusoids with precisely the same frequency omega as the original source. In each case, omega is the same, 1 gigahertz in our example. What is different, though, for each voltage and current as we move through the circuit is that its magnitude and phase will be different. The voltage of each sinusoid we see in the three linear elements will be different from each other and different from the original source. Likewise, the phase that we see for each of sinusoid that describes will be different than the source and of course different for each other. Same thing for the currents when we see there. We know there's a sinusoid of frequency omega at every location. The only thing we don't know for each element is what is its magnitude and what is its relative phase. Now that we understand sinusoids and the fact that they are the eigenfunctions of linear time invariant circuits, and what that means is they aren't distorted by a linear time invariant system. We excite a sinusoid or excite a linear time invariant circuit. For example, with the sinusoid of a frequency of 1 gigahertz, we will find that we get a sinusoid, a frequency of 1 gigahertz every single place, the eigenfunction of those circuits. Let's do a little more highfalutin math here and move into the realm of complex numbers. At first, this may not seem like it has anything to do with what we're studying, but we'll find that, in fact, it is very important to the concept of sinusoids. And so we look at the concept of Euler's equation. Euler said that if we take an exponential and the argument of that exponential is a purely imaginary value, a value j times phi, phi being an angle, as we'll see in a second here, that the result is a complex number. Again, the argument is purely imaginary, j phi, phi being a real value, j phi therefore being purely imaginary. The result is a complex number which has a real part equal to cosine of phi and an imaginary part which is equal to sine of phi. And so we can go through here and look at the different complex numbers that results from different values of phi. If we have phi is equal to 0, we find we get a complex number which is 1 plus j0. And again, this is important. It is a complex number of 1 plus j0. Of course, 0 times j is 0, and 0 plus 1 is 1. And so mathematically, we see that either j0 is equal to 1. But one of the things you want to keep in mind, and students lose sight of this and can confuse them, is that ultimately 1 is a complex number. A 1 is a complex number with a real part of 1 and an imaginary part of 0. What we're going to do in this class, as we'll see in a second, is pretty much express everything in terms of complex numbers. Sometimes they don't look like complex numbers. For example, if we say 1, but what we're really saying when we say a value of 1 is a complex number with a real part of 1 and an imaginary part of 0. And we see that right here. Let's say for phi, instead, we get a value of pi over 2. When we insert that into Euler's equations, we get a complex number which is 0, the real part is 0, plus j times 1. Of course, 0 plus j times 1 is j times 1, and 1 times j is, in fact, j, the square root of minus 1. And so we can say from Euler's equations that either j pi over 2 is equal to j. Likewise, if phi is equal to pi, we can show that it's a complex number, which is a real part of -1 and imaginary part of 0, and therefore we can, by getting rid of this part, 0 times j is 0, 0 plus -1 is -1. That's a mathematical fact, but again, we want to keep in mind what we're saying here is that it is a complex number with a real part of -1 and an imaginary part of 0. If we go to 3 pi over 2, we find that we get a complex number of 0 minus j, or just minus j. Notice in all these cases, we find if we take the magnitude of these complex numbers, we get a value of 1. And this leads us to the complex plane in terms of sort of analyzing these results. Any complex number we can plot as a point on the complex plane. Since as a real and imaginary part, it's basically a Cartesian representation, and we can take the x and y axis and assign it to the real and imaginary part and plot points, complex numbers, on the Cartesian plane, on a two-dimensional plane. Of course, another way to plot points on a Cartesian plane is using polar coordinates. In polar coordinates, instead of talking about the distance from the x-axis or the y-axis or the distance from the x-axis, we define a point by simply the distance from the origin, and that is the magnitude, we say, of that point, the magnitude of the complex number, and then an angle, which is a rotation angle from the real axis that's positive, the rotation angle all the way around until we bump into that point. So we have an alternative way of describing a complex number. We can talk about its real and imaginary part, again, sort of Cartesian, x and y, or we can talk about it in terms of its magnitude, its distance from the origin of the complex plane, and its angle phi, which is the rotation from the real axis as we move along. Again, really just a polar plot. Done this probably since grade school, going through, or at least middle school, plotting points on the Cartesian plane in terms of x and y, or in terms of polar coordinates, magnitude, distance from the origin, and rotation angle phi. And so we can do the same thing for complex numbers. Notice in this case, the magnitude, as we said, for every one of these is 1. So we can go through and write any complex number in terms of its magnitude, the distance from the origin, and its angle, the rotation, again, from the real axis there. And that is written from Euler's equation. I probably should have written this more generally. If I were to say, let's say, a times e to the j phi, then a times cosine phi plus j times a times sine phi would be the result. A would be the magnitude of that complex number, meaning the a would need to be a positive real value, and phi would be that angle, or that phase angle. Notice this is not some notation. This is not a phasor notation. This is precise mathematical statement. The value 1 is a complex number that has a real part of 1 and an imaginary part of 0. But also 1 is a complex number which has a magnitude of 1 and a phase of 0. Likewise, j is a complex number who has a magnitude of 1 and a phase of pi over 2, rotation angle of pi over 2. Minus 1 is a complex number which has a magnitude of 1, not minus 1, a magnitude of 1. The magnitude must be positive, and an angle, a rotation angle of pi. Minus j, of course, magnitude of 1 and a rotation angle of 3 pi over 2. And so in this course, it's very helpful to go back when we talk about complex numbers and talk about the real and imaginary part, but we'll find that it's even more important to talk about a complex number in terms of its magnitude and phase, this angle phi that we have. And we express that complex number in terms of Euler's equation, the magnitude times e to the j phi, where phi is that phase angle. You want to memorize this plot and memorize these results. We'll be using them over and over again in this class, and it's important that you can go back and forth very quickly without really having to spend much time thinking about it. They become just something that you know, as opposed to something that you have to look up. Trust me, this will save you a lot of time and grief as we move through this class. Now let's put these two pieces together. This idea of a sinusoid, which is the eigenfunction of linear time invariant circuits, and this Euler's equation now that we've been talking about. Notice in both places we've been talking about a magnitude and a phase. A magnitude and phase of the sinusoid, now a magnitude and phase of a complex number. Is there some way we can glue these two things together? Well, if we go through and let's say that we write now cosine of phi being some angle, some phase. Of course, that now is the real part of cosine phi plus j sine phi. But of course, cosine phi plus j sine phi is complex exponential e to the j phi by Euler's equation. In other words, we can write our cosine operator, the one that showed up in our sinusoid, as simply the real part of a complex exponential e to the j phi. Now, this seems like a very complex way of trying to write a sinusoid. Again, it's like writing the value of 1 as 1 times e to the j 0, or minus 1 as 1 times e to the j pi. And to a certain extent, that is true. But this complexity actually will end up making things more simple for us. Because let's say we insert now for this angle phi the argument of our cosine in our sinusoid, omega t plus phi, a phase which is proportional to time with the proportionality constant of omega, the radial frequency. When we insert this into here, we see that we can rewrite our sinusoid, our general sinusoid for the voltage at some or across some linear element. We can rewrite it in this way. Look what we did here. We said the cosine of this argument is simply the real part of the complex exponential with that same phase argument. But here's the great thing. E to the x plus y is simply e to the x times e to the y. And we're going to take advantage of that point to separate now the argument and the cosine, so that we have one term which involves only the relative phase phi sub n, and another term which involves simply the omega t part of the phase. We've been able to extract this phase from this argument. And why do we want to do that? Well, that phase is unique to the element itself. It changes from linear element to linear element to linear element in our circuit, whereas omega, as we found, is the one constant value. Once we know it for one element, we know omega for every element. And so we've pulled out that unknown value here. And so we can write our complex exponential, our sinusoid, I should say, a function of time. We can write it as the real part of the product of four complex values. The final complex value is a function of time, but note these first two complex values are not a function of time. They are dependent on the magnitude of the oscillation at that point in the circuit and the relative phase of the oscillation at that point in the circuit. If I multiply these two complex numbers together, I get a complex number. And I've mapped the two parameters that are unknown, or variable, I should say, for each element in the circuit, the magnitude of each location and the relative phase of each location. We've mapped them into one complex number. That one complex number really tells us everything we need to know about the voltage at that location, or if we're talking about current, the current at that location. We can take those first two complex values, which were not a function of time, and multiply those complex values together, and of course we get a new complex number. You multiply two complex numbers, you get a complex number. And let's call that complex number complex voltage, V sub n, which describes, we'll find, the voltage across some circuit element n, a complex number. If we look closely at this complex number, there's even more good news for us, because that complex number is expressed as some real value times e to the j phi. Well, that's exactly how we write a complex number regardless of it's a voltage or current or any other complex number. By Euler's equation, if we write a complex number as some number times e to the j phi, what we're saying is the magnitude of that value, a complex number, is the first value, and then the phase, of course, is the argument in the exponential. We look at this and we see that this is then the magnitude of this complex number, and this value is the phase of this complex number. But what is V0n? B 0 n, as we've seen right here, mathematical. Again, this is not mathematical notation. This is not phasor notation. This is mathematical equality. This is, in fact, the correct answer for a complex number, and has a magnitude and a phase. The magnitude of this complex number turns out to be simply the magnitude of the sinusoidal oscillation at that element n for the voltage. Likewise, the phase of this complex number turns out to be the phase, the relative phase of the oscillation of that voltage at element n. This mapping is therefore straightforward and direct, almost too straightforward and direct. I think students sometimes miss the mapping because it's so trivial and easy. We describe with a complex number a sinusoid. In other words, we're trying to describe its magnitude and its relative phase. We know the frequency, it doesn't change. We need to know the magnitude and relative phase. How do we extract the magnitude and relative phase from this complex number? Well, it's pretty simple. The magnitude of this complex number is the magnitude of the oscillation. The phase of this complex number is the relative phase of that oscillation. It's straight mapping from the mathematical domain into the domain of a sinusoid. We don't have to take the square root or divide by 3 or do any kind of machinations in terms of the mathematics to extract those values. Simply a straightforward extraction. Magnitude of the complex number is the magnitude, phase is the phase. This is a very important concept that it is crucial that you understand. And as I've taught this course, or courses similar to it, over the years, I found that students sometimes are lacking in the understanding of what they're doing. They understand they're trying to manipulate math and get complex numbers, but what do those complex numbers actually mean? Remember, if we're using complex numbers to describe a voltage or a current, which is what we do, what we're really doing is describing the magnitude and relative phase of the sinusoid for that voltage or current. And therefore, complex voltages and complex currents, when we use them, mean that we are using a sinusoidal source. Almost certainly then we only describe voltages and currents with complex numbers when we are describing signals within a linear time invariant circuit, one that is excited by a sinusoidal source. And so we look at our circuit here, our original circuit, and instead of writing down voltages as a function of time, we simply describe the voltages and currents at each location in the circuit with one complex number. If I told you that I2 is equal to J, for example, oh my gosh, what does that mean? J, it's imaginary. You mean it doesn't exist? The current is 0? No. J is a complex number whose magnitude is equal to 1. The oscillation I2 has a magnitude, therefore equal to 1. J is a complex number whose phase, e to the j pi over 2, its phase is equal to pi over 2, 90 degrees. And therefore the relative phase of that current oscillation is 90 degrees out of phase with respect to the reference at time t is equal to 0. That's true for each current complex number describing the voltage in relative phase, a different complex number, different magnitudes, different phases. Likewise for the source and the voltages that we find, each of them will have a different complex number, each one describing the magnitude of the oscillation and the relative phase. Again, it seems kind of confusing to students sometimes, I can tell, because we're using complex numbers and real and imaginary and magnitude and phases, and this all seems highfalutin mathematically, but it's just a way of being able to describe ultimately what we know to be true with the sinusoid, and that is it has a magnitude and it has a relative phase. We extract those two values from the complex number, those two real values, and we know exactly how our sinusoid is behaving at that location. All the analysis we do, we find it's very easy to manipulate these complex numbers to find those answers. Once we find the complex numbers, the currents and voltages at different locations on the circuit, we express them as a complex number. Now, we could take those complex numbers and convert them back into sinusoid, real values, functions of times, which is what they physically are. And we probably should do that more often. But because that transformation is so trivial that typically we don't do it. We just leave it as a complex number. eventually students sort of lose track of the fact that those complex numbers are describing the magnitude and relative phase of a time harmonic oscillation, a real value with respect to time. Computer scientists and engineers are always talking about their compression algorithms, that you can take information and compress it into a different form and then extract it later. But electrical engineers have compression algorithms too. In fact, ours have been around for a lot longer. And one of them are this Euler expression of a sinusoidal function. We describe currents and voltages in a linear time invariant circuit as complex values. If we really want to know what the real physical representation of the voltage and current is at that point, we need to apply our compression algorithm, our decompression algorithm really. We need to take the complex number and take its magnitude, and that tells us what is the magnitude of the oscillation. We take that same complex number and we extract its phase, and from that, that tells us the relative phase of the oscillation with respect to the reference. And so we always, excuse me, we always go through and write voltages and currents in terms of complex numbers. But what we're really doing, always keep in mind, is we're simply describing a sinusoidal function with time, a sinusoidal function of frequency omega that has a certain magnitude, a real value, positive value, and a relative phase. Again, a sinusoidal function, there are three unknowns: the magnitude, the frequency omega, the radio frequency omega, and the phase, or three parameters, I should say, for a sinusoid. We talked about magnitude, relative phase. What about omega? Remember, omega doesn't change from element to element to element in a circuit. It is the frequency of the original excitation. Once we know it at one place, we know it every place. And that was the great thing about applying complex analysis with Euler's equation, is it really allowed us to separate the unknown phase from the known value of either j omega t, the time varying portion, but varying with respect proportionally to omega, which is a constant across all elements in the circuit. And so typically we don't, from a complex analysis, ever write either j omega t. We know it's always there. We can always put it back in. We know the source. We know what omega is. Multiply by the complex number and take the real part and get the sinusoid. We can always do that. But again, because we can, we typically don't. We just write voltages as a complex number and currents as a complex number. And what we'll find from that, we can pretty much figure out all the things that are of interest to us. For example, things like the rate of energy absorption, power. For example, we don't have to write it in the time domain. We can extract it directly from these complex representations of voltage and current. To reiterate what I just said, this basically is the representation that we use in this class. We always assume linear time harmonic circuits. We always assume sinusoidal excitation, and therefore we can describe the current and voltage every place in those circuits in terms of complex numbers. We have a magnitude and phase that map directly into the magnitude and phase of the sinusoids at that location. So we'll talk about a complex number here for current and voltage at every spot, but remember how to convert that back into a real value of time if need be. Okay, let's do a little quiz just to see if you've understood what I've talked about here. If you're viewing this video on YouTube or something, I would pause it right now and go through and see if you can answer each of these questions. What we're doing is talking about a voltage across some linear device in a circuit, and we've represented that voltage as a complex number. And the question is, what is the sinusoid that it actually is describing? Remember, complex numbers have magnitude and phases. The magnitude of the complex number is the magnitude of that oscillation of that sinusoid. The phase of that complex number is therefore the relative phase. So it's a pretty straightforward operation to do that. Despite the fact that it's straightforward, it causes confusion for a lot of students. And let's look at some of this, all right? So I assume you've paused and gone through and figured out the answer for all of these at this point. If you have not, go ahead and pause and finish it up. And let's go through the solutions and see what they are. Now, first of all, look at this first one. The voltage equal to 3. And what I find in this course, and it frustrates me a great deal, is students over and over again decide that if I say the voltage is equal to 3, that we're talking about a DC voltage of 3 volts. It's just 3 volts sticking there at a time. In radio engineering, there are no DC voltages. They aren't very useful to us. Okay, sure, we have bias voltages for devices and such. But in terms of the circuit analysis, the high-frequency circuit analysis, all right, DC is not a high frequency. DC is a frequency of exactly 0. And we're talking about in this class frequencies that are going to be in the megahertz or the gigahertz in frequency, high frequency changing. There are no DC voltages that we'll talk about in this class for the most part. And so when I say the voltage is 3, what are we talking about? First of all, every voltage is a complex number. And when I say the voltage is 3, I'm saying that the voltage is one whose real value is 3 and an imaginary part is 0. Now that's interesting. The real part is 3 and the imaginary part is 0, but it's not very helpful to us. When it comes to voltages and currents, they're all complex numbers. Instead of describing them in a real part and imaginary part, which they all do, instead we describe them in terms of magnitude and phase, and that is the physical description of what's going on. A complex number that is equal to 3 has a magnitude of 3. Remember, magnitudes are always real and positive. And so if I take the magnitude of this complex number, 3 plus j0, I get a magnitude of 3. That is the magnitude of oscillation of this sinusoid. What about the phase? Well, 3, of course, is equal to 3 times e to the j0. E to the j0 is equal to 1, and therefore e to the j0, 3 times e to the j0 is simply equal to 3 times 1, or 3. 3 is a complex number whose magnitude is 3 and whose phase is equal to 0. 3 times e to the j0. And that's the thing you should do in your mind. Anytime you see a complex voltage or current is rewrite it in that Euler form. 2 times e to the j pi over 2. 4 times e to the j pi. That tells you exactly what the magnitude is and that phase is. And again, this is not notation. This is not phasor notation. 3 times e to the j0 is exactly equal to 3. It's not a notation. It is a mathematical equality to 3. If we go down to the next one, this is the second most problematic that I see in the course. The voltage V1 is equal to J. V1 is purely imaginary. A real part is 0, an imaginary part is 1. Oftentimes students will say, well, if the voltage is imaginary, it must not really exist. The actual voltage, V1 as a function of time, must be equal to 0. Again, we're not doing the decompression algorithm properly here, are we? V1 equal to J. J is a complex number who has a magnitude, and the magnitude of J is 1. What is the phase of J? If I were to rewrite J in terms of Euler's expression, some magnitude times e to the j phi, I would write it as 1 times e to the j pi over 2. Therefore, the voltage V1 is equal to J is describing a sinusoid whose magnitude is equal to 1 and whose relative phase is pi over 2, 90 degrees. These two operations are crucial for this class. Over and over again, I see students that will define this as a DC value of 3 and define this as a DC value of 0. No, in both cases, they describe a sinusoid. Source is 1 gigahertz. Both of these are sinusoids of 1 gigahertz. In this case, a magnitude of 3 and a phase of 0. In this case, a magnitude of 1 and a phase of pi over 2 are 90 degrees. Make sure you can do that transformation and make sure you do it quickly. All right, go back and look at that page where we have the unit circle and we talked about e to the j 0, e to the j pi over 2, e to the j pi, and so forth, and go back and forth. So let's look at, let's say, this one. V3 is equal to minus 2. Once again, this is not a DC voltage equal to minus 2. This is a complex number. What is the magnitude of this complex number? Oftentimes students will tell me the magnitude of this complex number is -2. Well, that's not the case. Magnitudes of complex numbers must be positive. They're real and positive. The magnitude of -2, not the absolute value, the magnitude of -2 is +2. What is the phase of -2? Well, that's the phase of -1, which is pi. E to the j pi is equal to -1, and therefore -2 is equal to 2 times e to the j pi. The magnitude of the oscillation, therefore, is 2, and the phase is pi, or 180 degrees. Make sure you can go back and forth in this analysis. This last one, let's do this one down here, V5. This is the general case, and hopefully this will show you how simple it is to convert from complex numbers to their sinusoidal representation if you write the complex number not in terms of its real and imaginary part, but in terms of its magnitude and phase. Write it with respect to Euler's equation. Again, this is not a notation. This is not phasor. This is mathematical equality. I have a complex number which is 3 times e to the minus j pi over 4. That complex number has some real parts. That complex number has some imaginary part. We're not really very concerned with that with respect to sinusoids. The real part and imaginary part doesn't help us much. What we're interested in is what is the magnitude of this complex number. Well, it's 3. And therefore the magnitude of the oscillation of voltage 5 is 3. What is the relative phase? What is the phase, rather, of this complex number? Well, it's minus pi over 4. And therefore the relative phase of that oscillation is minus pi over 4. And of course the phase here we can write in 2 ways, either from 0 to 2 pi, 0 to 360, or we can write it in terms of minus pi to plus pi, minus 180 to plus 180. And of course with the periodicity of cosines, it doesn't matter which one that we use. So make sure you can do these and understand what the complex values are telling us. It seems simple. You probably did this a few years ago in your classes, but what I find is students know that voltages and currents can be written as complex numbers, but have a hard time mapping those complex representations in what is physically true. And what is physically true are these sinusoids oscillations with respect to some very high frequencies in our class, frequencies omega.